Hello, I'm Felix Hartmann from Interekt and Associate Editor of Quantitative Plant Biology.
Hello, I'm Mélanie de Courtet from University Clermont-Auvergne. Today we will show you how differential geometry can be useful to describe the gravitropic motion of a plant organ. We will take the plant stem as an example. After a plant stem has been tilted horizontally, it bends upward to restore its vertical position. How can we quantitatively describe this gravitropic movement? Traditionally, this has been done by monitoring the inclination angle at the shoot tip. But a given tip angle can correspond to very different stem shapes. So, how to get a more complete description at the organ level? A solution is to monitor additional inclination angles. For example, at the base of the stem, or at various positions along the shoot. Here, S denotes the spatial coordinate along the organ from the base to the tip. Pushing this strategy to the limit, we get the distribution of angles all along the organ. You may wonder how to monitor so many angles. Don't worry, this can be automated using some specific software. For example, the free software Interekt. If we are actually interested in the global shape of the stem, the relevant information is not the value of the angle, but how the angle is changing along the stem. In other words, we are interested in curvature. In common language, curvature means a lot of different things. Mathematically, the curvature is defined as the rate of change of the inclination angle along a line. It is the derivative of the angle with respect to the spatial coordinates. For a straight stem, the inclination angle is uniform, and therefore the curvature is null. If the stem sits along a circle, the rate of angle change is uniform, and therefore the curvature is also uniform. It is equal to the inverse of the circle radius. Unlike angles, the curvature does not depend on the reference frame. In addition, the curvature does not depend on the length of the organ. Now we can look at how the curvature changes during the gravitropic movement. But has the curvature some biological significance in the gravitropic response? The gravitropic response is essentially a change in local curvature with time. This involves sensing capacities. Until recently, it was thought that only the inclination angle was sensed by the plant. But a modeling approach demonstrated that inclination sensing was not sufficient to explain the gravitropic movements and the final posture of plant. Plants are also able to read their own shape to grow straight. This means that plants can sense their curvature and respond to it. This is called proprioception and is essential for the gravitropic response. Using Interekt, we can measure how curvature varies in space and time and visualize it as a heat map. In this experiment, the plant is first tilted horizontally and bends downward under its own weight. Its curvature is slightly negative, as indicated here by cool colors. After half an hour, the shoot tip starts bending upward. Its curvature becomes positive. Colors get warmer. Then the whole stem bends upward and its curvature increases everywhere. The curvature reaches a maximum and the tip overshoots the vertical. Then the curvature decreases a bit and the shoot apex comes back to the vertical. We hope you are now convinced that curvature is a powerful tool for describing gravitropic motions.